Right. Thanks. That's kind of the most touching, impressive introduction I've ever got before. Really appreciate it. Yeah. I would like to talk about my research for past couple of years, and also actually my research agenda for next few years. And actually, when first asked me to present at this IRIM seminar, I kind of underestimate the workload. And yesterday night, I realized that I want to change the story a little bit, organization of my existing research slides. So actually, I just rewrite the entire introduction yesterday, which takes much longer than I expected. But I would like to share just some thoughts and the story in my mind, and so that I can let you know that where are we and where we want to go. Right. Let's start by checking the state of the arts. So where are we? I am not too expert. I'm mostly doing leg locomotion research, so I'm not too familiar with other types of robots. But I think that these are pretty much perceived as some sort of the state of the art. For instance, manipulation. This can be one of the state of the arts, right? Hand manipulation, solving the Rubik cube. We're solving one Rubik cube by one hand is still pretty impressive. This is done by OpenAI. But yeah, still not as agile as the human, right? Human records are like, what, 3 seconds, 4 seconds? Still much slower than that, but very impressive. Navigation. I'm not sure. There are tons of the navigation work, so I just pick one from my favorite colleague, Alexandra Faust at Google. This is her team's work. This navigation robot navigating with all the moving obstacles. Actually, this is kind of the core kitchen at the Googleplex. So really, Jeff Dean drinks coffee here. It's like the most popular place, and this navigation robot can, a weird robot can navigate while avoiding obstacles, moving human. This can be some sort of viewed as one of the most impressive approach. You can see that the scenario has been changed, but still you can avoid the obstacle nicely. This is good, right? And then what's next? Drone. Let's not skip over the drone. So this is a paper called Deep Drone Racing. I'm not too familiar with drone racing, but it passes all the gates based on its vision sensor, looks stable. So I think this must be one of the state of the art, and it do pretty nice stable flight with pretty good intelligence. This is the work for the state of the art for drone. Then what about the legged robots? Well, this is one of the most recent paper from CMU collaboration between the Facebook and the CMU, which is called RMA, Rapid Motor Adaptation. Now the robot can walk over the very bumpy terrain. That small quadrupedal robot can walk on this uneven terrain. It can step down the stairs on a hiking path. So really, this is one of the most impressive work, and this is published at this year's RSS. But when I say the state of the art, I bet many of you come up with this video, stunt of the Atlas. Presented by Boston Dynamics. It can, walk over the obstacle, jump over gaps, step down the stair, like do many parkour-like stuff. By the way, I'm not sure that you are familiar with this, but they have really bad tradition of posting their video right before the ICRA deadline to just frustrate the other researchers. Really, they are bad guys. But my point is there, yeah, this is super impressive, right? A humanoid, we all know that the humanoid doing that kind of the agile locomotion is super, super hard problem. I know that. But is this enough? That's the some direction we want to go. I would like to show the state of the art in nature, in the sense that the little dog, see the agility of this little dog. I believe this one is much more agile than any existing robot. With its vision sensors, it can overcome many different obstacles. Very robust, no failure, maybe failure, but it can recover. Self-maintained, super, super agile. I don't think we are not there yet, definitely. But actually, okay, let's wait just a couple more seconds, then we're done with this racing. Okay, that's his or her record. It's super impressive. But actually, I would like to make my point here. I'm not saying that this agility is something we want. Actually, the dogs are more than fast racers. Actually, they are. You see, maybe we focus on the just agility, but actually that agility is combined with the many other features, like many other intelligent decisions, careful motor control. It's different from they are different from the fast racers. And I believe what we want is not just fast racers. We want to see more impressive stuffs. Like this one, rescue dog is playing piano. Right, then to do this, what do we need? Like we need more, various motions with nice hand-eye, hand-paw coordination, right? Know the context should not hit the piano too hard. So this one is the very good example of the more intelligent behavior. And I have a friend at Google whose name is Jay, and Jay and I our dream is train the robot dog to fetch beer from the refrigerator. So this is different from the just the fast racing, right? This dog open the refrigerator, fetch the beer, and grab it and back to us, which means that it knows how to manipulate things. It needs to calibrate itself using just the vision sensors. Must understand the context. Must maybe understand some language. It can be, I'm not sure what is the trigger. It can be verbal language. It can be our body language. I don't know, but definitely. We want something more intelligent than now. And that's the research goal of our lab, at least for, I would say, 5 years until my tenure. I think this will be the research agenda for our lab. So to develop intelligent leg robot that can make human life better. I don't want them to be, just working on the simple trade. Trade is fine. Walking robust locomotion is fine. But really, can it make human life better? Maybe yes, maybe no. But I really want them to do more meaningful things. And I believe that we need more intelligence here. So by saying more meaningful things, I mean few things, like the last mile delivery, like the robotic dog is delivering some item from here to there. For instance, I'm kind of the lazy person, so I hope that my robot dog delivers the food from the tech square to my office at Klaus. I don't want to walk like 20-30 minutes to pick up the burrito from Moose. Or they can be a lifelong companion for human, like they can do more close human-robot interaction. They can support human. They can do emotional support. I think the robotic dog has great potential. And also the one thing I really want to do is developing a guide dog. I think the robotic guide dog has pretty high potential. Of course, guide dogs are expensive to train, right? We cannot do mass production of the guide dogs. And also the robotic guide dog, they can see the world with their visions, and they can combine with any other AI technology. They can explain what they are seeing. Usually dogs don't talk human language. So the robotic dogs, they can explain something to us and communicate with us with verbal language while providing the same service as an animal guide dog. So these kind of things can make our life better. And these are some research agenda of our lab. Most tools-wise, of course, we are very interested in the deep reinforcement learning, which is a pretty effective automated tool for developing highly intelligent agent. We all see those bright achievement, like the game of the Go, that AlphaGo versus Lisetter. I watch all the games live, and I'm so sad that Setter lost. But yeah, that's kind of the big showcase of the deep reinforcement learning. And also autonomous driving. Sometimes they are developed based on the manual script, but sometimes many of them also leverage the deep reinforcement learning as well. So deep reinforcement learning will be the tool a good tool for us for many years at least. So I would like to highlight this one. So today, I would like to talk about a few things. First, I would like to discuss the deep RL for locomotion first. Although I want to do many cool stuff, I cannot just start it right away. First, for leg robots, we first need to learn some useful locomotion. Particularly, I'm interested in the overcoming sim-to-rear gap by leveraging the real-world data. I would like to I conducted a series of the work in this direction. That's the first thing I would like to discuss, and then I would like to discuss some more behaviors, how to learn more behaviors, and I would like to discuss navigation while understanding the real-world environments. Before we begin, by the way, please interrupt me at any time. I would love to hear your questions. Right. Let's start with the first line of research, which is the learning to walk via deep reinforcement learning. Right. So basic idea is simple. Just we want to train the locomotion on by deploying the deep reinforcement learning in the real world. Why? So biggest hurdle for deep reinforcement learning is that the simulation optimized controller often do not work on hardware, which is so-called a sim-to-rear gap. So this is the policy in simulation, but if we directly deploy this, then it falls immediately, and it burns motor for high chance. And some real world actually even tougher for simulation. We cannot easily simulate them. For instance, this is the memory foam with the 3 inches, which has some deformable body with memory. It's memory foam. There's some memory in its dynamics. Or it's Doormat. It has all the complicated texture. It's also deformable. We cannot simulate everything in the virtual world. So one of the big philosophy at Google is that directly train on the real world. Learning on real world is intrinsically free from the sim to real gap. For instance, my colleagues at the Google, they train the tossing bot by just how to toss the object by using the real world experience. And I had a small project that is training the policy on the real world for this small reconfigurable robot. This is the automated training environment, very simple gadget, but it can train the effective locomotion in the real world. No simulation data, but directly learn from the real world. But actually, deploying the deep reinforcement learning on real robot is not straightforward. Basically, on top of the existing challenges, we must consider two agenda. First one is the sample efficient learning algorithm. In simulation, we can use like millions, billions of the samples, but real world numbers are much smaller. And the second is we need a safe and automated learning system. Otherwise, it requires a lot of manual human intervention, or it will break the robot or surroundings. But if successful, this is the one illustration of the learning process. This robot is so-called a Minotaur, which is a very small quadrupedal robot, planar structure, 8 degrees freedom, 2 dots per each leg. Within a few minutes, I would say 1.5 hours, it collects all the experience and start to how to move forward. So I believe most of you are familiar with reinforcement learning, but in short, just in case, reinforcement learning agent is trying to maximize the reward by interacting with the environment. Agents do some action to the environment, and it changes state, and the environment evaluates the quality of the motion by giving the feedback with the reward. This is a simple one-line summary of the reinforcement learning. And there's a framework of the maximum entropy reinforcement learning, which optimizes for both expected return and the entropy of the policy. So which means that actually this formulation says that, hey, you should achieve the task, but at the same time, you should maintain certain minimal level of the policy entropy to explore more wider variety of the situations. And this promises us better sample efficiency and more robust policies. And here's our algorithm, soft Actor-Critic with learned temperature. So basically, we modify the existing soft Actor-Critic algorithm. We formulate this entropy term as the constraint, and then we change the constraint maximization to its due using Lagrangian formulation. In a nutshell, we do not care about the entropy if the current exploration is enough, but we start to care about the entropy term a lot more if our exploration is not enough. So this term alpha here, this term alpha will be automatically adjusted. And it turns out that our algorithm outperforms all the existing baselines. Like, when was it? This was like 2019, and at the moment, I think many of them are actually still the kind of the state of the art. It outperforms the baselines, DDPG, TD3, PPO, SEC with a fixed temperature by regulating the policy entropy. This is one of the benchmark tests. You can see that it achieves the higher reward, while maintaining on the right-hand side, you can see that they are maintaining the entropy at the right level. And it turns out that this algorithm works surprisingly well on the real world. definitely it can work on the learn to walk on the flat ground. This is the same as the training environment. But actually, due to the structured wider exploration, it is pretty robust. It can walk on the slope, a very unstable platform, or it can walk down the stair, which never seen during the training. All right, this is the one part about the one challenge, which is about the algorithm. But unfortunately, at the moment, we didn't have the scalable and safe learning environments. So actually, it requires the human intervention for like 2 to 3 hours. Sometimes we need a cooling time. It was painful to do experiments. Well, a scalable learning environment, if you imagine, is much easier for manipulation, right? It's fixed, so you can reset to any position at any time, and there's no big safety issue. But it's really more challenging for under-actuated leg robot. We have to deal with many challenges. I can show them some examples. I can show you some examples. Like it can. Oh, I didn't know that sound is on. It can dive forward, right? And it actually burns the left front motor very quickly. Or it can flip to the sideway. I'm not saying that it's jumping to flip. It actually oscillate left and right very gently and start to flip over. And it's leg robot, right? So definitely it can step out of the bounds and start to hit the fence. And also it can get tangled with a cable, so that then it starts to hurt the learning process, because that cable kind of contaminate the collected samples. So we fix everything using some gadgets. Sometimes they are developing some policy. Sometimes they are developing some algorithms. Like we add an additional safety constraint to the RL formulation. Now we have the additional safety constraint, which means that we want to keep the failure rate to 0. And it can be also solved with the same approach, Lagrangian relaxation. It turns out that this promises us the much lower failure rate compared to the fixed rate, while achieving the reasonable performance. And also, we do the automation using the multitask learner. Simply, we learn interleave the forward and backward learning depending on the robot position. If the center is in front of the robot, we try to learn the forward locomotion. And if it's same here, but if it's backward, then we try to learn the backward locomotion task. But actually, this simple tool kind of minimize the number of the failures, number of the case where the step out of the bounds. And this is the heat map of the task in the 2D, and you can see that they are kind of attracted toward the origin. We also developed the recovery policy that can automatically reset from the wide range of the states. We just developed it manually, but it takes some time. But actually, it never fails. It kind of always successful. It can always successfully make the robot get up from the fallen position. So with all the inventions, actually, we can reduce the number of the human resets from 89 to 0, so which means that you don't need to lift that 8-kilogram robot 89 times. Instead, just you unbox the robot. Theoretically, you can unbox the robot to the ground, wait a couple of hours, then you will get the locomotion policy. So this is like the early exploration. But if we fast forward to the later, then you can see that they start to move a much more longer distance. And here are learned policies. Like this is the forward gate, and this is the backward gate. I like that they come up with a slightly different locomotion style depending on their foot structure. Now, if we record the initial motivation, we want to do learning on real robot because of the challenging terrain that are very hard to simulate, right? This is the initial exploration on the memory foam, one of the challenging terrain, and this is the state after a few hours. And then it gives us a pretty nice policy for forward one. It's doing kind of the mixed, I would say it's something like the plonking gate, but not quite the same, right? Backward policy is more like the energetic pacing gate. And we can repeat the same experiments on the doormat, do the initial exploration. And after a few hours, we see some improvements. Then it gives us the nice forward gate. I like actually this movement when the leg stuck at between crevices, and it tried to pull it off. And I believe this kind of detailed behavior would not be able to get with simulation. Backward policy, somehow it's still kind of the very energetic pacing gate. It's almost flip over, but it doesn't. Another benefit of the learning directly from the real world is that we can actually learn the turning gates as well. So here the problem is that a miniature robot has the planar structure. So it's really hard to design the nice, effective turning gates because in simulation, everything is perfectly symmetric, right? We cannot learn the nice turning motion in simulation. But in real world, it kind of exploits the slight difference between the left and right, slight mass distribution. So then we combine everything all together. We just learn we can control the robot using joystick. So it's like once again, you just unbox the robot, you define some tasks, then after a few hours, you're coming back from your work, then the robot, we will be able to control the robot using joystick. All right, but so until now, we learn everything in real world. So there's no simulation data at all. But is this the best way we can do that? Do the learning? Where still simulation will contain some useful information. So instead, our recent work, we start to pre-train a policy in simulation and try to fine-tune in the real world. Still, the idea is same. We kind of mix-learn the forward and backward policy, but we just use the pre-training. Of course, we made some changes for fine-tuning. First one is instead of doing simple locomotion, we take the imitation learning framework. So this is a very nice work of the Jason Peng, which is to imitate the given reference motion. A green one is the reference motion, and the left-hand side is the simulated one. We use the similar framework. And second thing is that we fine-tune, we pre-train in simulation using SEC, but we fine-tune with the red Q, which is a randomized ensemble double Q learning. This technique key idea is to learn a random ensemble Q function, it's model-free, but it turns out that it's actually faster than model-based RL like the MBPO. Honestly, we are still do not 100% understand why red Q is so fast. But the other intuition is that it prevents the overestimate or the underestimation problem of the Q function nicely, and of course that's kind of one of the reasons. But anyway, it's super sample efficient. And third thing is that we learn agile and robust reset controller in simulation. So instead of using manually designed reset controller, we train the reset controller using deep reinforcement learning. And it turns out that it resets in very agile way, which is like the 5 to 10 times more faster than the company provided get-up controller, and also the very robust in the real world. So with these changes, our new version of the framework, now we can go outside. We go to the backyard, and we try to fine-tune the pre-trained policy. This is the little bit scaled version of the existing work. And after a few minutes, we start to see some improvement. And here's comparison. Like the pre-trained one, it does not go forward that much, but the fine-tuned one, it can go forward very nicely. Backwards, same. The pre-trained one can still go backward, due to the shape of the legs. But if forward at the end, while the fine-tuned one, it can go without falling. They are also actually better than we think this fine-tuning has a lot of potential. There's many existing way of doing some sort of the fine-tuning in the real world. For instance, using meta-learning, or you can some sort of train with the latent variable and fine-tune those knobs in the low-dimensional knobs. But we compare our method with the exact or the existing RMA or the latent space tuning. We believe ours is the best, but we will see. We will keep working on this research direction. All right, so this is until so far our progress in the deep RL for locomotion. All right, so by the way, any questions? Sure. Safety constraints, that's a good question. Safety constraint, we measure the certain dangerous scenario, like the center of mass goes below certain threshold, and we try to avoid those situations.
So do you borrow this safety constraint from the constraints people use in PC or in the
No, it's pure deep reinforcement learning.
But speaking of the
MPC, actually, thanks for bringing that up. So because now I will talk about some sort of the manual control and also the hybrid approach of the deep reinforcement learning and the model-based control from now on. So I would like to talk about how to learn more useful and expressive behavior. So as I show you in the early slide, this is the robotic movement, and the natural movement must be much more than that, right? This is just, even without their outlooks, if we just we demonstrate some sort of the skeleton of the same motions, we can easily tell this one is robotic and that one is with a rear. We can easily tell. So what do we need for more natural motion? That's something I would like to talk for next 5 to 10 minutes. So actually, I would like to share some our recent work. This is the collaborated work with Facebook. First answer TNU will join our lab pretty soon. The title of the work is the model-based motion imitation for agile, diverse, generalized quadrupedal robot. But in short, we want to develop the model-based control for doing more imitating natural dog movements. That's the main topic of this paper. So deep reinforcement learning offers a convenient way for imitating the imitating the given motion. The mimic paper of the Jason made a lot of impact in computer graphics and the robotics community. It's good, but it often not transferred to the real robot clearly. Robot falls down if we don't take care of the sim to real very much. And also another downside is super data hungry. It takes up to like around 100 million steps. And for single motion, I'm not saying about imitating entire behavior. For learning single motion, it takes like 100 million steps, and it's quite significant amount, I would say. So in this paper, we discussed the question like, can we directly develop a model-based control that can imitate the given motion? So which means that we don't need any learning. Just we develop the controller, and the same controller can do all the different motions like turning, trotting, pacing, sidestepping. Just a single controller is enough. And actually, I don't want to say we solve all the problems, but actually we were able to achieve pretty good preliminary result. So big core part of this work is the model-based control, how to control the robot to follow the given motion. And also the second important component is the trajectory optimization. Because the motion capture data, sometimes there's some obfuscating, there's some artifacts. We want to fix those artifacts using the pre-processing, at pre-processing stage using trajectory optimization. I don't want to dive too deep into the mathematical equations. I would like to give you some high-level intuitions, like the first rule. Compute the right contact forces to track the given center of mass for the current contact force for each foot. When they are contact, we can apply some force. If they are in the air, then we can apply the force from the foot. This is the rule number 1. And rule number 2, we adjust the feet positions if the robot moves too fast or too slow. That's it. This is inspired by the very traditional Weber style controller. But combining the rule number 1 and rule number 2, we were able to achieve the certain good tracking performance on real robots. And second is we want to clean up the reference motion using the trajectory optimization. We clean up the given motion. We use we fit the dynamic movement primitive, DMPs. And as you can see in this flap below, the blue ones are with DMP when you fit the motion with the DMPs, and it shows the much better tracking performance to the ground truth, which is the gray one. Results are pretty. I like the current results. In simulation, actually, same model-based controller can actually track all different types of the motions, and actually they are even better than the reinforcement learning baselines. And not even in simulation. They can kind of deploy to real world. We didn't have a good chance to work that with the SEs with the deep reinforcement learning, but our model-based control is kind of robust, so that it can do many things in the real world as well. And once again, there's no pre-training, just a single controller to do all different types of the motion. So actually, I think this might be some interesting research topic: data-driven model-based control. And actually, I would like to highlight another collaboration for this time. It's collaboration with Google. This one is about the visual locomotion. So basically, to do more useful stuff, we have to do natural hand-eye coordination. Otherwise, we cannot do meaningful things. But in the context of the locomotion, how can we negotiate challenging terrain using vision inputs? This robot here, we have the 2 vision cameras here and here. One is facing forward, one is facing down. and see if we can overcome some challenging platforms. Here, the key idea is combine the deep reinforcement learning with the model-based control for sample efficiency. So, deep reinforcement learning for feet-eye coordination per se, and a model-based control for low-level control. And this combining the model-based control, it gives us the much better sample efficiency. It gives us the better learning curves. That's the whole spirit of this project. By the way, there's also another really important topic, sim-to-real transfer. So, as I said, applying the deep reinforcement learning for real robot, always there's some drawback of the overcoming. It's basically, we have to overcome the sim-to-real gap. So here, we identify that a lot of the sim-to-real gap come from the vision inputs. Here you can see that the rear left-hand side, you can see that the rear and the sim images, they are different. And also, we have this small band, which is the occlusion due to the robot's body. So we add the noise and do some painting those regions, and we downsample it, applying some additional filtering. Then we get these images, and they have the smaller gaps. And then we evaluate our approach on the variety of the complex terrains. I will just show you a couple. Like the first one is the step stones. There's slight small gaps, but we can adjust footsteps to overcome them. Or we can work on those pores, which is quite hard to work on, and their heights are randomized. We can, by replacing the low-level controller, we can also overcome them with a slightly different style. And we can overcome a lot more challenging cases, like the moving stepstones. Or we can on the curvy pores again. So it requires pretty nice eye feet coordination. We can deploy our method for the real world as well. See, it can work on the stepstones. And it can also walk up the platform. Probably you all know that sometimes it fails in the real world. We don't want to hide our failure cases. Sometimes due to sim-to-real gap, it fails, and we need those safety gadgets to prevent further disasters. All right, I would like to jump into the last topic, which is about the navigation. So basically, I wonder if those robots can understand surroundings to do more meaningful tasks. So actually, I said navigation, but actually the navigation is some sort of the narrow topic. It's really about the understanding surroundings, so that it can do some meaningful stuff. For instance, something as doing something in kitchen. I believe there are many industries like Toyota, NVIDIA. They are all working on their kitchen environment. Yeah, because it's so crowded. It requires a lot of the manpower to do house chores. So this is a very challenging workplace for robots. I've been working on the navigation of the robot for throughout actually a few years. I tried the different approaches. First one is the imitation learning, but the data collection on robot is kind of cumbersome. So I tried to to imitate the navigation of the real human. So what I did was I asked my intern to mount many different cameras on his body and randomly walk the room for many times. It gives us this kind of the merged perspective demonstration. And then we kind of try to extract some meaningful information from this merged perspective data. Basically, we have to translate this to the robust perspective. For more details, please refer to the original paper. But it turns out that actually we can learn successful navigation policy out of this multi-perspective human demonstration. The navigation distance is still quite short. It's kind of the proof of concept, but still it can find some desired image based on without any from the unstructured human motion data, human demonstration data, without any prior knowledge. And also, we tried the deep reinforcement learning. We won the I-Gibson challenge by combining two approaches. First one is the scalable deep reinforcement learning from habitat and doing sim-to-sim transfer to the I-Gibson simulator. And also the domain-specific data augmentation. Basically, we add a lot more people than usual. And actually, it gives us the pretty nice performance. A baseline without no augmentation is unsuccessful. It hits the human a lot. But with our method, we augmented with a lot more people, and it can successfully navigate between the humans and get to the final destination.
But I would like to highlight our
recent project, which is the learning to navigate the sidewalks in outdoor environment. Because this was challenging. This is directly connected to the last mile delivery. But also at the same time, this was surprisingly challenging, I would say. Can you guess like those challenges? I've been doing mostly indoor navigation, and I thought, okay, what can be the additional challenges for outdoor? We simply changed our environment from indoor to the outdoor. It turns out that a lot. We have to deal with a lot more sensor noises, unstructured context, lighting has been changing, constantly. Sun keeps moving. Sometimes different weathers. No 3D scans. We don't have the specific scan data of the target environment. We all need to go to new scenes. No guidelines. It's nothing like the autonomous driving. There's some guideline. Cars are moving with a certain organized way. There's no guideline. Just humans walk wherever they want. And many more. So this was very challenging problem. So we have to come up with some better way to learn the more intelligent agent. I would say our key approaches can be summarized as two. First one is the learning by cheating. This framework is developed by the Chen et al. Like a couple of years ago. A big key idea is that first learn a teacher agent with privileged information, which cannot be accessed by the typical robot. It's kind of the cheating. So really like knowing all the position of the nearby cars perfectly, and then we do the cloning once again to the student agent which is so-called the sensory motor agent in the original paper. Student agent has with the realistic sensors. We apply the same technique for our framework, but our teacher agent is now learned by the deep reinforcement learning. We first learn a capable teacher with a privileged information, such as a bird's eye view, something like this. And so basically, it knows the surrounding context perfectly. And then we clone this agent. This is with the more visual inputs here, with the egocentric visual inputs. So we clone the learned behavior to student agent. This is the one thing, one key technical component of this project. And the second component is the sim to rear. Basically, we have to find the sensing modalities. Previously, we all know that we kind of know that including more sensors are helpful when we do the deep reinforcement learning. But for this case, it is not. Sometimes we add a sensor that they introduce a lot more noise, and we know that the deep reinforcement learning is vulnerable to extrapolation. So we need to investigate different sensing modalities, including RGB, depth, LiDAR, semantics, and the semantic features, which is kind of the a layer between the right before the inferred semantics. And so eventually we find out that the combination of the GPS, LiDAR, and the RGB semantic is the best combination. How can we do this? We really did a lot of experiments. For instance, we test them in the rear outside work. This is the left-hand side is the feature agent ours, and its success rate is really nice. And the color agent is bumps into the step out of the bounds or the bumps into the object. See the numbers on the left-right corner, and the semantic agent is really vulnerable to the sim to rear gaps. And with all of the combining these techniques, we were able to walk the many trails in the city of the Atlanta, in combined more than the 3 kilometers. Here are the fast forward, a few successful trials. Still, they need some certain amount of the human intervention, like a handful, I would say, 5-ish per each trial. But they can actually, they surprisingly work well in the real world. They can follow, they can avoid oncoming humans. Yeah, they can really navigate the totally unseen environment without that much of the problem. But always in robotics, really fun part is the failures, right? They occasionally face due to many reasons, like it includes the failing semantics, drifting, or the GPS issues. Also the driveways, sometimes it confused with the driveways, so try to follow the driveways instead of the sideways. So really there are a lot of failure cases, but still, yeah, we're kind of doing good. And sometimes I think, yeah, let's wait a little more. Then sometimes, yeah, they failed due to battery issue, I guess. But it's fine. Our robot can still do a great job. So in summary, our lab is working on the more intelligent leg robot. We aim for better visual motor control, including navigation, and also we aim for more expressive locomotion, not just robust locomotion. We want to do more meaningful interaction with the environment and the human. And that's it. Thanks for your attention. So your question is the leg robot and the rear dogs have different body structures. So still even they are the same. I think the semantics of the motions are quite transferable. So in that sense, the imitating motion, achieving the dog level of the inspired by the dog motions, try to achieve their expressiveness, their locomotive behavior. I think it's, first of all, it's very meaningful problem. At the second time, I wish that we can have the next version of the leg robots. They become more, similar to dog with head, necks, spines, and tails. That's what I want to see, but I'm not really expert on designing new robots. So actually, I'm just requesting my colleagues to please give me more natural-looking robots. Thank you.
I'm curious about the repeatability. So, for example, for RL, if you run the same experiment next time, will you kind of like learn different types of gates, or will it kind of be a very similar game?
Or will it kind of be a very similar?
Reproducibility is actually a hot issue in academia because some paper reports this number, and if we deploy we try to replicate their work, then we actually don't get the same performance. But it's really kind of the hard problem. So actually, there's a lot. First of all, I would like to kind of defend all the researchers because there's a nice paper called Implementation Matters. So basically, the small details matters, part in reinforcement learning and also the robotics. So we try to share all the details. Actually, people and the entire community put a lot of effort on sharing details, like open sourcing hardware, open sourcing the code. But still, sometimes it's really hard. And also, I would like to highlight another effort. So in that sense, some other researchers, they try to investigate more offline learning. So basically, they train only using the offline existing data, just like the classification problem. But honestly, I understand their point, but I think as a big fan of the robots, I think just whatever we can do with the real robot, then actually it speaks itself. So I think that's some sort of the big topic we need to face for many years. Yeah, but I'm not sure what is the really big answer for that question.
So can you speak up a little more?
Sorry, can you speak up a little more?
Is there one particular policy that your system prefers to for each robot? Or are there multiple different policies that can work, like their own style of gauge?
I'm not sure the which. So basically, you're asking us.
I'm not sure the which. So basically, you are asking us we can do single policy control or the multiple policy control, I guess.
So really, it depends on the different projects.
So really, it depends on the different projects. Sometimes we train the one control policy for everything. Sometimes for instance, the learning on real robot project, we train the different policies for forward and backward gates, and we kind of have the gating policy to select which one is which one. Or sometimes we can kind of fuse everything into one big policy using behavior cloning. So there can be different coordination depending on the project.
If I train the multiple times,
if I train the multiple times, we get the same gates. No. No, really no. Sometimes it really depending on our reward function design. Sometimes the one gate has a large region of attraction. So every time I rerun the learning, it converges to that specific gate. But sometimes it converges to very random different things depending on the definition of the task.
That's the question.
That's a good question. Typically, we just generate the target join position.
So you use another.
Sometimes, actually, I would like to correct myself.
Sometimes, actually, I would like to correct myself. Sometimes the join level position, but sometimes the high-level command to the low-level MPC controller. So both cases. And actually, we can do, but actually, I need one more correction. For Miniature robots, is the really low motor control signal, like the current to the motors. So it's really it can be viewed as the torque control. So it can do anything. By the way, I would like to share one thing. This is a little bit off from my research itself. But actually, I'm seeing interesting trend in the leg robot research. My folks and the IT companies, they are experts in the deep reinforcement learning, and they start to try to learn about the model-based control because they are kind of frustrated about the performance of the deep reinforcement learning, and they think by combining more prior knowledge, they can make their learning better. I see one trend there. And on the other hand, I'm seeing my model-based friends at the model-based control community. They are they are intimidated by the recent progress of deep order community, and they are trying to learn the deep reinforcement learning to make them better. So really, the different community, they are trying to learn from each other. I think the next few years, I think there will be a lot of the interchangeable research topics, like interdisciplinary research topics in the community. So I think that trend is very interesting in the community.
The last thing David said, I hope you heard it, and I hope it occurs to you that if you're interested in this from any perspective, talk to people who are interested from the Georgia Tech, places filled with folks that are thinking about the same kinds of problems, but from different points of view. And if you don't take the chance to talk to those folks and learn what's going on, you'll have a very narrow view. The reason to be here is because of the diversity of inputs. Lunch is back there as usual with Thanksgiving. Lunch is back there as usual with Thanksgiving.
Oh.
So thank you for the great talk. One good question was, in case you have an unexpected situation in which the robot suffers a damage, like an arm gets amputated, in that case also do you think a model?
So you are talking about when the robot is kind of broken?
So you are talking about when the robot is kind of broken? Still, I think we can do both, deep reinforcement learning and model-based control. I don't want to limit the approach to one. Actually, there's some work like I skipped some parts, but I have some preliminary work using meta learning, like when not the amputated, but when the one motor becomes very weak, then how can you react to those situations? Deep reinforcement learning, you can do it with meta learning. Model-based control, I think you can still just try to estimate what's going on and do MPC, then probably you will be able to react to the given situation. Thank you.